Equivalence of parallel postulate. Hey, I've been thinking about this equivalence of parallel postulates thing we discussed in class. It's kind of crazy how one little postulate, like the parallel postulate, can change the entire structure of geometry.
Totally. And what's even cooler is how in neutral geometry, when we leave out the parallel postulate, we can still explore some parts of geometry. But once we start considering alternatives, we can flip between Euclidean and non-Euclidean geometries. It's like a choose your own adventure book, but for geometry.
Exactly. So let's break it down a bit. Euclid's parallel postulate says that given a line and a point not on that line, only one line can be drawn through the point parallel to the original line. But there are other ways of thinking about it too, like Playfair's axiom, or even the triangle angle sum theorem. It's wild how they're all equivalent.
Yeah, Playfair's axiom is basically the simplified version of Euclid's postulate. I also find the triangle angle sum theorem super interesting. It's so normal to think of the sum of angles in a triangle being exactly 180 degrees, but it turns out that's only true if the parallel postulate holds.
Right, and without a parallel postulate, we get a non-Euclidean geometries. In hyperbolic geometry, for instance, the sum of the angles of a triangle is always less than 180 degrees. So that changes everything. No wonder people struggle for centuries trying to prove that parallel postulate.
True, it's not something you can just prove using the other axioms, it's independent. Oh, and remember the Sakiri quadrilateral? That figure is such a clever way of exploring the different geometries. Depending on the summit angles, we can determine whether we're in Euclidean, hyperbolic, or elliptic geometry.
The Sakiri quadrilateral blew my mind. If the summit angles are right angles, we're in Euclidean geometry, but if they're acute, we're in hyperbolic geometry, and if they're obtuse, it's elliptic. It's like geometry shifts depending on the type of angles.
Exactly, and this all goes back to the equivalence of the parallel postulate. With other theorems like the alternative interior angle theorem, it's so interconnected. You reject the parallel postulate and suddenly, alternative interior angles don't behave the way we expect them to in Euclidean geometry.
I love how this shows the parallel postulate's importance. It's not just random rule but really what holds the structure of Euclidean geometry together. Without it, the whole system changes. Not Euclidean geometries are just as valid but they feel so different.
Yep, understanding how all these postulates are linked really opens up a whole new view on geometry. It makes me appreciate how flexible and dynamic geometry can be, depending on which assumptions you make.
Absolutely. It's like we're stepping into a whole new world of possibilities once we start tweaking these postulates. I've been thinking about the parallel postulate. Why do you think it's so crucial in Euclidean geometry compared to neutral geometry?
Great question. The parallel postulate essentially defines the behavior of parallel lines in Euclidean geometry. Without it, in neutral geometry, we can't guarantee that certain theorems such as the alternate interior angle theorem hold true.
Interesting. But what if we can't prove those theorems without a parallel postulate? What implications does that have for our understanding of space?
It shows that our conception of space isn't as straightforward as it seems. In non-Euclidean geometries, like hyperbolic or elliptic, the rules change completely. For instance, in hyperbolic geometry, the sum of the angles in a triangle is always less than 180 degrees. That changes how we think about shapes and sizes in different spaces.
So would you say that the parallel postulate is a fundamental assumption that shapes the entire structure of geometry? How does that impact mathematical proofs and theorems?
Exactly. The parallel postulate is like a foundational pillar. If we alter it, we're essentially creating a new framework for geometry. This raises the question, Can we ever prove the parallel postulate using other axioms? If not, what does that say about the nature of mathematical truths?
I think it suggests that some truths in mathematics are inherently different depending on the axioms we accept. Speaking of which, why do you think mathematicians have historically focused so much on trying to prove the parallel postulate?
I believe it's because they were seeking a unified understanding of geometry. If they could prove the parallel postulate from other axioms, it would reinforce the coherence of Euclidean geometry, but failing to do so led to the discovery of other geometries, which open up a whole new realm of mathematical thought.
That makes sense, and the Zachary quadrilateral really illustrates this well, doesn't it? By explaining its properties, we can see how different angles lead to different types of geometry.
Exactly. If the summit angles are right angles, we're in Euclidean territory. If they're acute or obtuse, we've ventured into hyperbolic or elliptic geometry. It's fascinating how one figure can connect all these different concepts.
So, how do you think understanding these equivalences influences fields outside of pure mathematics like architecture or physics?
Well, in architecture, for instance, knowledge of different geometries can help in designing structures that must account for curvature and angles, especially in large-scale designs. In physics, especially in theories related to space-time, understanding non-Euclidean geometries could change how we view the universe.
I love how geometry connects to so many areas. This makes me wonder if the parallel postulates can lead to different geometrical systems, what other fundamental assumptions in mathematics might be similarly powerful?
That's a thought-provoking question. I think exploring those assumptions could lead us to new discoveries and a deeper understanding of mathematical concepts across various fields.
Angle sum of a triangle. Have you thought about how the angle sum of a triangle can be different depending on the type of geometry? I used to think it was always 180 degrees.
Yeah, I remember learning that is Euclidean geometry, but things change in neutral geometry, right? The angle sum of a triangle doesn't necessarily have to be 180 degrees anymore.
Exactly, in Euclidean geometry, you use the parallel postulate to prove that the sum of the angles in any triangles is 180 degrees. You can extend a line through one of the triangle's vertices, and by the parallel postulate, you can form an alternate interior angles that add up to 180.
But in neutral geometry, we don't assume that parallel postulate, so we can't guarantee the same angle sum. The best we can say is that the sum is less than or equal to 180 degrees. That's where the Sakiri legendary theorem comes into play.
Yeah, neutral geometry is kind of like a halfway point. It works for both Euclidean and hyperbolic geometries. For hyperbolic geometry, the sum of the angles is a triangle is always less than 180 degrees. Did you know that larger triangles in hyperbolic geometry can have their angle sum getting closer and closer to zero?
That's wild. It's like the bigger the triangle, the more warp space gets. I read that the difference between 180 degrees and the actual sum is called the angular defect, and in hyperbolic geometry, it increases as triangles get bigger.
Exactly. That's what makes hyperbolic geometry so different from Euclidean geometry. And in elliptic geometry, like on the surface of a sphere, the angle sum is always greater than 180 degrees. Have you seen those triangles formed by longitude lines meeting at the North Pole? Their angle sum is more than 180 degrees.
That's so cool. I guess that's why it's used in navigation and astronomy, right? Because we live on a curved surface. So Euclidean geometry doesn't always apply when dealing with large distances.
Exactly. Different geometries give us different insights. It's fascinating how something as simple as the sum of a triangle's angles can vary so much depending on the geometry you work with.
Totally. And it makes you think about how geometry ties into the real world, like architecture using hyperbolic curves or maps that account for the Earth's curvature and elliptic geometry. Geometry isn't just abstract, it's everywhere.
I've been studying the angle sum of a triangle, and I find it interesting how it changes in different types of geometry. Can you explain why the angle sum is always 180 degrees in Euclidean geometry?
Sure, in Euclidean geometry, the sum of the angles in triangle is always 180 degrees due to the parallel postulate. When you extend one side of the triangle and draw a parallel line to the opposite vertex, you can show that the alternate interior angles are equal, leading to the conclusion.
That makes sense, but what happens in neutral geometry? Why can't we assert the same angle sum there?
Great question. In neutral geometry, we don't assume that parallel postulate. As a result, we can only state that the sum of the interior angles of a triangle is less than or equal to 180 degrees. The Sacchi-Legendre theorem explains that without the parallel postulate, the angle sum varies depending on the geometry.
Interesting. So can you give an example of how the angle sum behaves in hyperbolic geometry?
Sure, in hyperbolic geometry, the angle sum of a triangle is always less than 180 degrees. The larger the triangle, the more pronounced the angular defect. For example, if you have a triangle with very long sides, its angles can be quite small, reflecting the warm nature of hyperbolic space.
I see. Now, why do you think it's significant that triangles in elliptic geometry have angle sum greater than 180 degrees?
That's a thought-provoking question. It shows that geometry is not just about flat surfaces. In elliptic geometry, like on the surface of a sphere, the curvature affects the angles. For example, a triangle formed by an equator and two lines of longitude on Earth has an angle sum greater than 180 degrees. This has practical implications for navigation and understanding that the Earth's geometry.
Exactly. Speaking of applications, how do you think the angle sum theorem impacts real world fields like architecture or astronomy?
The angle sum theorem is crucial in architecture when designing structures that require non-Euclidean principles like hyperbolic paraboloids. In astronomy, understanding the curvature of the universe can influence how we study large-scale structures in cosmology. It's fascinating how these concepts are applied in practical ways.
Do you think these different angle sums can help mathematicians develop new geometrical theories or models?
Absolutely. Exploring the properties of triangles in various geometries can lead to new insights and theories. For instance, the relationships between angles and sides in different geometries can inspire innovative mathematical models and tools for solving complex problems.
This is really enlightening. Thanks for breaking it down. I feel like I have a better grasp of how the angle sum varies across different geometries.
Anytime, it's always great to discuss this concept. Let's keep exploring geometry together.
Thank you for watching.